Alright, so last time we were working on a pretty interesting problem, one that we had to break up into parts, take advantage of symmetry properties in order to compute the integral. And again, the main issue here stems from the fact that these regions that we typically work with are symmetric, and well, you have some area at the top and you have the same area below. So if you consider the signs of those values, well, technically those values cancel out, and well, all the page and a half work would be worthless if you get our final result equals to 0. And also that doesn't make sense at all. That's because, well, clearly there's some shaded area that must have some value. So what we did is find the area of half of the region and then multiply by 2. And furthermore, what we did is to split that region into two regions because of the sharp corner that we have in here. And let me really quick. So this sharp corner basically divides this into two regions. Well, not like this, never mind. Alright, so today we're going to look at another problem that has the very similar issue here. Well, so let's find the area of the region inside of the rows r equals to 6 sine theta, and inside the circle of radius to 3. Alright, so let's see what about this one. So number one, let's go ahead. Oh, by the way, there's a little typo here. This little typo right here, this should be r equals 6 sine 2 theta. Alright? Because only one theta, well, what are we going to see? Only one leaf. Well, that's technically not a flower, it's just a leaf. And in fact, it's a circle, not a flower in this case, not a row. So, let's see. So let's go to our graphing calculator. Make sure you are in polar mode rather. And type the two equations. So that's 6 sine 2 theta, close parentheses, and in your y2 there's the circle of radius 3, r equals to simply 3. Okay? Alright, so let's graph, and we're going to see this. So it's a flower, it's a rose with 4 leaves. Well, you could have guessed that from the coefficient that multiplies the theta symbol. It's an even number, and it's 2, and whenever we have an even coefficient, well, in this case, it's going to have twice as many leaves as the number that multiplies in the case that it's even, right? Again, that's not something I would expect you to memorize, but it's something cool as a pattern recognition to have in our, in our minds. All right. So this is what we're going to get here. And well, they're asking us to find the area inside of the rows and inside of the circle. Number one, let me do an illustration by hand. Okay, so we have the, okay, perfect. We have the circle of radius 3, which looks something like this, and we have the rows that looks like this. Alright. And well, so we want the area inside. So this is the area that we want. Okay, let me zoom in a little bit. This way, so you can see what are we really finding here. Oh, come on. This is what I wanted. So we want this area right here. And notice in this case, we want this area, also that area, also this area, and this area as well. Yes, my picture here is not perfect, but I mean, I think it's still easy to see what is it that we want to find. So, well, and so we don't have to do an integral from 0 to 2 pi, because do you see the areas above and the areas below? Those are the same values of the same areas. That's going to give us a 0 as a value. So no, we're not going to do that. Instead, we're going to do a similar process that we did last time. We are going to find only one of the areas and then multiply by 4. All right. However, okay, let me zoom in as an illustration here. Let me do only one. Only one of the loops here, and well, let me use the same colors we used before. That's part of the circle, and this is the other part of the graph, the loop, or okay. And well, we need to find these points of intersection using algebra. So we need to find, to do that, we set 6 sine theta equals to 3. We set the two equations equal to each other. R equals R, R1 equals R2, depending on the notation. Divide by, it's 2 theta, by the way, not theta. So that sine 2 theta equals 3 over 6, which is sine theta equals to 1/2, 2 theta. Well, so which angles have a sine equal to 1/2, by the way? So that happens when 2 theta equals to, okay, sine, which is opposite over hypotenuse. Is that a 30-degree angle? Or, well, in radians should be pi over 6. And then the next value, it's actually on the second quadrant. I believe it's 5 pi over 6. Okay. So those are the two values, 5 pi over 6. Well, but in this case, notice we are solving an equation for sine to theta, not sine theta. So we have to divide this by 2. Or rather, it's much easier to multiply both sides by 1/2 because of the fractions on the right hand side. Well, so that's theta equals to pi over 12 and 5 pi over 12. And of course, these are periodic functions. We can have many more solutions. These solutions are going to be the ones that are going to be in the second quadrant, and then tomorrow in the third quadrant, etc., etc. They go. So we're going to have infinitely many solutions due to the periodicity of these functions. Well, but in this case, since we are only interested in the values in the first quadrant, well, we only want this area right here. So let me trace those rays that actually, and you'll see what happens here. But you see how the area is going to get split in essentially 3 regions. So in the previous problem, we did it by splitting it into 2 regions. In this section, in this case, okay, let me zoom it in a little bit so you can see the colors a lot better. Okay, some good color here. Okay, let me use purple. So we are going to find the area, the value of this area right here, right? But notice this value of the area that I just highlighted with purple, by symmetry, isn't it the same as this value of this area right here? Isn't it the same? And well, why am I splitting the areas like this? Well, that's because of this sharp corner. Then we will have to do the same over here. So we would have to find the area of this region right here. All right. So we're splitting it into 3 pieces essentially. But I mean, in this case, what we're going to do is actually set up an integral within 2 pieces, because these 2 regions in pink are really the same, you know. So let's label them. Let's call this R1. This is R2. And this is R3. Technically, these three regions, but what we can just say is that R1 equals R3. So the plan for this integral will be, okay, always start writing, setting this up as a plan. So, plan. To find the total area, right? We should multiply 4 times whatever area this is described by one of the shaded regions, which at the same time, well, this is going to be 2 times the region 1, right? Because these two in purple are the same, plus R2. All right. Let's set up the integrals first, and from there, let's see. So, number 1. So R2. Well, actually, what do I have in here? Okay, I think. Okay. Okay, let's keep recording. So that means 4 times 2 times the area of region 1. Now, but do you see that in this case we have the integral of, okay, this area right here, the one in purple, it's bounded by the leaf of the flower. Do we all agree with this? I know sometimes it's hard to see because here when it comes to finding the area, we're not looking at top minus bottom, right? Like which is the height of the function, right? In this case, it's technically the height of the function. I mean, it's, you know, you can imagine like the rectangle, but recall that the rectangles in this case are not rectangles, are actually infinitely many circular sectors, right? So in this case, we have the integral of 1/2 the function squared with respect theta, and that function squared is 6 sine 2 theta. All right, and that's times 2. Oh, and the limits of integration are going to go from 0 to pi over 12. And plus the area of the region 2. Well, according to my older notes, I did it with the same function, but guess what? In this case, it's going to be a lot easier because this region 2, what is bounded by the region 2? Just a circle r equals to 3, not a crazy trigonometric function, which is great. So that's the integral of 1/2 times the function that describes the radius squared with respect theta. But in this case, the limits are going to go from pi over 12 to 5 pi over 12. Okay, and well, in this case, that function is 3. Oh my God, that's going to save a lot of work. Really. Okay, so let's first simplify these coefficients, and then we're going to write the problem in terms of an integral 1 and an integral 2 to simplify our work here. All right, so in this case, well, 2 times 1/2, that reduces to, okay, let me keep the 4 times first. So that's going to be simply the integral of 6 squared, which is 36, sine squared to theta from 0 to pi over 12. And plus, okay, this is going to be 3 squared, which is 9. 9 times 1/2 is just 9 halves. Nine halves the integral from pi over 12 to 5 pi over 12, and simply d theta. Okay? Yes?
Why is there a 1/2 in front of the function?
Oh, because that's the formula, that comes from the formula to find the area of a circular sector. Let me go back real quick to here. All right. So it comes from finding the area of a circular sector on the first page of the handout, and 1/2 times the radius squared times the angle, and then from there we construct via adding infinitely many areas of circular sectors, and then we get this integral. So that's where it comes from. And then, well, so okay, yes, let's simplify this. Okay, 4 times 36, oh, big number. 36 times 36 is 72. 72 times is 144, I think. So that's 144. Integral from 0 to pi over 12, and that's a sine squared to theta, d theta. And 4 times 9 halves, so 4 over 2 reduces to 2 times 9, that's 18. Integral from pi over 12 to 5 pi over 12 with respect theta. And how about we treat this as 2 separate problems to make our lives a lot easier. I1, I2. Integral 1, integral 2. Alright, so, well, let's work with integral 1 separately, I1. So, that's 144, integral 0 to pi over 12. And, well, we can write sine squared. Well, let's write the sine squared. Of course, we cannot use trigonometric, I use substitution here because, yes, we have a composition function, but we don't have the derivative of the sine function outside, so it stands the du part of the problem. So we're going to use the power reduction formula, which is, in this case, 144, 0 to pi over 12. That's 1/2. 1 minus cosine of 4 theta, right? And be careful when using the power reduction formula because we duplicate the angle. If it's already 2 theta, well, that doubles to 4 theta. And then, okay, 144 over 2, is that a 72 again? 72 times the integral from 0 to pi over 12. That's 1 minus cosine 4 theta. And I know we could have written the 2 integrals in one shot at the same time but I'd rather do one step at a time. So that's going to be 72 integral from 0 to pi over 12 of d theta minus 72 integral from 0 to pi over 12 cosine 4 theta d theta. And well, these 2 integrals are pretty straightforward. So we can 72 theta and minus 72 times 1/4 sine 4 theta evaluated from 0 to pi over 12. Alright, so well, let's simplify. 72 over 4, is that, I think, 18? 72 theta minus 18. Where did I? Oh, yeah, that's minus 18 sine 4 theta, valuing from 0 to pi over 12. And as usual, upper limit minus lower limit. This is going to give us 72 times pi over 12 minus 18 sine 4 times pi over 12. That's upper limit. Minus lower limit. Well, the lower limit, do we all agree that it's going to give us a big 0 here? Because if we plug in 0 for theta times 72 is 0, and sine of 4 times 0, which is still sine of 0, it's going to give us a big 0. So that's fine. This notation is fine if you do it on the exam or anywhere. And 72 over 12, is that a 6? 6 pi. And then we have 4 over 12, which is pi over 3. Pi over 3, so minus 18. Sine of pi over 3, so pi over 3 is 60 degrees, and sine is root of 3 over 2. And 18 over 2 will be 6 pi minus 9 root of 3. So that's the first result. The result of the first integral. Let's have a look at the second integral. Okay. Let me have everything for the first integral. Second integral. which looks like the integral of 18. Well, this one is pretty short. 18 pi over 12, 5 pi over 12, d theta. So the integral of d theta is simply theta. That's 18 theta evaluated from pi over 12 to 5 pi over 12. And I split it into two separate integrals because the limits of integration are different had we had otherwise the same limits of integration for all integrals. Well, in that case, let's just, let's have everything into one single expression. So that's 18 times 5 pi over 12 minus pi over 12. And well, 5 minus 1, that's 4. 18 times 4 pi over 12, which reduces to pi over 3, which is 6 pi. Right? And well, we're ready to express the whole area. That in terms of I1 plus I2, and this will be then 6 pi minus 9 root of 3 plus 6 pi, which reduces to or combines to 12 pi minus 9 root of 3. Final answer. Okay. The next and last topic, actually, arc length. Well, so arc length in polar coordinates, again, this is one formula that you want to put on your notes, so, and everything is going to be given for a problem like this. I mean, you will be given to find the area along, not the area, the arc length along a given polar function, a flower, a limosome, a cardioid, or like this one that we have here, which is called the logarithmic spiral. And the limits of integration are just going to be given. It's not something that you will have to figure out. It's not like in the area problems that you will have to set up the equations together, solve the equations so we can get the points of intersection, and then from there figure out the limits. And actually in those cases in which we need to set up in terms of more than one integral. All right, so these ones are different. And well, so we're asked to find the arc length of the logarithmic spiral given by the function within the limits negative 2 pi to pi. All right, so let's just use the formula. Actually, we need to input in the formula, we need to input both the function squared and its derivative squared. Okay, so let's find the derivative of this function dr d theta. Well, the derivative of an exponential is always itself, e to the theta over 6 times the derivative of the exponential, which in this case is 1/6. And let's just write the 1/6 in front of it. Okay. Alright, so let's just set it up in the formula that we have above. So L equals the integral a to b r squared plus dr d theta squared d theta. And that's the integral from negative 2 pi to 2 pi. And well, you might be thinking, well, can we multiply by 2 and integrate from 0 to 2 pi? Not always, not in every case. So have a look at the graph of the function, which is, well, e second ln to get the e function theta over 6. If you notice, this graph is not symmetric about any of the axes. So in this case, we cannot use symmetry properties to rewrite the integral as 2 times from 0 to whatever angle. So it works, for example, maybe for a flower like we did before, or for a circle. I mean, just integrate maybe from 0 to pi and then multiply by 2, depending on what we want to find. So in this case, well, it's a whole different situation. So square root of r squared, that's the function e to the theta over 6, quantity squared, plus the derivative, be careful, 1/6, e to the theta over 6, also squared with respect to theta. Well, let's simplify this exponential e to the theta over 6 quantity squared. So recall that power of another power, powers multiply, and well, we're going to multiply 2 times pi over 6, all right, which reduces in this case to the square root of e to the theta over 3, all right? And for the second term, be careful because we have a coefficient and we have an exponential function, so we need to raise both terms. That is, actually, let me leave some room here. You'll see why. And that will reduce to, whoop, what happened here? Okay. Yes. Plus 1 over 36, because we square also the coefficient e to the theta over 3. And these two are alike terms, all right? How about LCD 36 over 36? So 36 over 36 plus 1 over 36, isn't that 37 over 36? And I'm going to write it in the following format for a good reason, you'll see. That's the integral from negative 2 pi to 2 pi. And that's the integral of 37 e to the theta over 3 over 36 with respect theta. Well, actually, you know what? Instead, let's do 37 over 36 like this. So let's look at the expression inside of the radical as a product of two quantities. Number one, the coefficient and the exponential term. So in this case, we can use the product rule for radicals. And well, that's going to be the square root of 37 over 36 times the square root of e to the theta over 3 with respect to theta. Well, let's simplify one thing at a time. Number one, we can use the quotient rule on the first factor, the 37 over 36. But in this case, it's only the denominator that has the perfect square. That has a perfect square root, rather. So this will be the square root of 37 over 6. And well, we can rewrite this radical containing the exponential function using rational exponents. That is e to the theta over 3, the whole thing to the 1/2 with respect to theta. So what are we going to have in this case? Well, so let's take out the constants outside. Square root of 37 over 6, integral negative 2 pi to 2 pi. And power of another power, multiply the powers. This will be e to the theta over 6 with respect theta. All right. So let's see. Let me see what's in my notes. So for the u sub part, u equals theta over 6, du equals 1/6 d theta, and d theta equals 6 du. All right. The limits of integration, we don't need to change them because I mean it's not gonna do anything really interesting. You'll see. So this time we're good with that. So this will be the integral, or rather square root of 37 over 6 integral of e to the u times 6 du, and notice how the 6's go away. Square root of 37 e to the u, and well, not yet, and that's square root of 37 e to the theta over 6, evaluated from negative 2 pi to 2 pi. And as usual, upper limit minus lower limit, that's going to be simply the square root of 37 e to the 2 pi over 6 minus e to the negative 2 pi over 6. And this reduces to square root of 37 times e to the pi over 3 minus e to the negative pi over 3. And this is an okay answer. Right? Oops. This is a final exam question. Right? All right, let's do one more. Okay, this one, it's going to help us. It's going to help us review a lot of the algebra here. Algebra and what else? The trigonometric identities. We're going to find ourselves into a pretty interesting situation in which whatever limits we put for the integral that we are about to set are not going to work, so we will have to think a little bit differently for this. Okay, so number one, find the arc length for the complete cardioid. R equals 3 minus 3 sine theta, right? And well, when they ask for the complete, it's one cycle, you may think of integrating from 0 to 2 pi. What could go wrong about integrating from 0 to 2 pi? I mean, that's one term, but in this case, we'll have to do something weird. Okay, let me just draw that cardioid for you real quick. So we are essentially finding the arc length of this graph. All right? And well, we need to find the derivative. R prime equals the derivative of 3 is 0 minus the 3 times the derivative of sine. That's a negative 3 cosine theta. And L is the integral from okay, let's say from 0 to 2 pi for now. Okay, let's set it up like that. That's the integral of the original function squared, 3 minus 3 sine theta squared, plus the derivative quantity squared with respect to theta. Well, we have a binomial square. We can use the binomial formula, the binomial expansion formula. So that's the integral from 0 to 2 pi. The square root of, that's a 9 minus 6. Oh, no, that's 3 times 3. That's 9 times 2. That's 18. Plus 9 sine squared theta, plus, because this negative quantity which is getting squared, it will become positive. That's 9 cosine squared theta. I know the integral looks a little bit crazy, but trust me, this is what we're going to do from here. You might want to observe the following. From here, 9, we can factor out a 9, sine squared plus cosine squared. What is that equal to? This is an identity equals to 1, 9 times 1, which is 9. Alright? So this 9 combined with this 9, it's going to give us an 18. Okay, so L equals the integral from 0 to 2 pi. The integral of 9 plus 9, that's 18, minus 18 sine theta, d theta. Okay. And well, of course, we can simplify this integral because notice we have a common factor of 18. However, we can factor out a 9 to write this integral in a lot simpler terms. You know, like, so we can use square root. So that's the square root of 9 times 2 minus 2 sine theta. Why didn't I factor out the whole 18? Well, because I would rather factor out at least one of the perfect squares, which in this case is the 9. So the square root of 9, which is 3, times the integral from 0 to 2 pi times the square root of 2 minus 2 sine. Okay? This looks ugly. Zero to 2 pi, square root of 2 minus 2 sine theta. Okay. So here's where the fun begins for this integral. Let's have a look about any strategy to go about it. Any ideas on this integral? Would use substitution work? Would use substitution definitely is not going to work because, I mean, we need a factor of the derivative of the quantity inside of the radical, more specifically a cosine, and then from there do the u du. And well, so we're in trouble here. So unfortunately, we cannot just multiply by cosine and divide by cosine to make that work. So what we're going to do here is to multiply by the conjugate, by the trigonometric conjugate, which is a technique that we discussed almost at the beginning of the course when we went back to more in-depth integration techniques. All right, so that's the integral from 0 to pi, 2 minus 2 sine theta. And what we're going to do here is to multiply numerator and denominator by the conjugate of 2 minus 2 sine. What's the conjugate of 2 minus 2 sine? 2 plus sine. 2 sine, right? So 2 plus 2 sine theta. Alright. And of course, don't forget that this is with respect to theta. So this is what we're going to do. In the numerator, we're going to combine the radicals in the numerator and we're going to leave the radical in the denominator alone. But here, this is the last page of the handout. So that's why I opened another page in here to continue the integral here. And I need a good color here that actually contrasts. Okay. Okay. Perfect. So that's the integral from 3 times the integral from 0 to 2 pi of the square root of 2 minus 2 sine theta times 2 plus 2 sine theta. The whole thing divided by the square root of 2 plus 2 sine theta. Alright? With respect theta. So one thing that you might want to observe, well, of course, from here inside of the radical in the numerator, our number one thing to do, maybe to FOIL, but notice this is of the form of a difference of squares. You have a backwards difference of squares, something like a minus b times a plus b, which is the same as a squared minus b squared. We can do that instead of FOILing. That way it doesn't take too long. That's the square root of 4 minus sine squared, or minus 4 sine squared, over the square root of 2 plus 2 sine theta. Alright, now we have a common factor in the numerator, in the radical in the numerator, that is 3 times the integral from 0 to 2 pi, and that's the square root of 4 minus, or rather 4 times 1 minus sine squared, and that's 2 plus 2 sine theta. Okay, we can take the square root of 4, which is a 2. And then what is 1 minus sine squared? But I mean it looks like we're making the integral even more complicated than it initially was, right? However, using the trigonometric identities, trust me, this is going to be pretty simple, you'll see. So I think we can recognize this 1 minus sine squared. What is this? Cosine, right? Cosine squared, because this one comes from the fact that sine squared plus cosine squared equals 1. If we solve for cosine squared, we get that 1 minus sine squared. Alright? So 3 times 2, which is actually 6 at this point, that's the square root of cosine squared theta. And now, well, the radical cancels with the square, isn't it? However, keep in mind that we're finding the square root of a quantity squared that is variable. So in the first place, this should be expressed as the absolute value of cosine. Alright, that's what we have to express it like initially. And then consider the integral, or rather the interval of integration. So in this case, because we're integrating from 0 to 2 pi, that is, it's a positive interval, well, we can just get rid of this absolute value. See, it's fine. However, if otherwise we were integrating, say, from negative pi over 2 to negative pi over 6 otherwise, well, in this case the interval of integration is in the negative side, so we would have to consider its other counterpart, in this case the negative. And now look at this integral. Can we evaluate this integral now? Yeah. Because now we have that derivative. It doesn't matter where the radical is this time. What matters now is all this tricks that we did is to get that factor of cosine that stands the du part of the problem. Alright, so let's do the u substitution to run into another situation, so to speak. Alright, so that's to cosine theta, and well, this is straightforward substitution. Just cosine theta d theta equals 1/2 du. So that's going to give us the following: 6 over 2. This is the half. Integral from, okay, that's a du over the square root of u, and we need to change the limits to the world of u in this case. U of 0, u of 2 pi. That's 2 plus 2 sine 0, and on the other hand 2 plus 2 sine 2 pi. Did you see the issue here? Oh, that's the integral from, the limits are the same. The integral from 2 to 2. Well, what's the integral from 2 to 2 for any function? 0. This is weird, isn't it? Because we're going around that cardioid, it's impossible to have a 0 arc length, right? So, well, here is where we need to have a second thought about it. Well, this is clearly not going to work. Well, so let me write down the region of integration again, real quick. So in this case, we're going to do the following. We are going to integrate better color. We are going to integrate over half of the region, but instead of going from 0 to 2 pi, what we're going to do is go from negative pi over 2 to pi over 2 and times 2. How about that? All right. So, well, in the first place, again, let me also scrap this integral as well and redefine 6 times the integral from negative pi over 2 to pi over 2. And in this case, I know negative pi over 2 and pi over 2 are symmetric values, but the region of integration is not. So in this case, we cannot use that another multiplication by 2. So in this case, this is cosine theta 2 plus 2 sine theta d theta, and this quantity times 2. Okay? So this will be 12 times the integral from negative pi over 2 to pi over 2 cosine 2 plus 2 sine, and let's do another u substitution. I know it's basically the same, but I don't want to go with the one that I already scrapped. So that's a u equals 2 plus 2 sine du 2 cosine d theta, and cosine theta d theta equals 1/2 du. And now let's change the limits. U of negative pi over 2 and u of pi over 2. Okay, so that's 2 plus 2 sine of negative pi over 2 and 2 plus 2 sine pi over 2. Okay, what's sine of negative pi over 2? Isn't that negative 1? Okay, negative 1 times 2, that's negative 2 plus 2, isn't it a 0? And sine of pi over 2, now we're above, that's positive 1 times 2, that's 2 plus 2. Better? Now we're going to get somewhere. So that's going to be 12 times the integral from 0 to 4 of du over square root of u times 1/2. I'm going to write down outside of the integral, and that's going to be 6 times the integral from 0 to 4, and that's u to the negative 1/2 du, and general power rule, that's a 6 u to the 1/2 over 1/2 from 0 to 4. But dividing by 1/2 is the same as multiplying by 2. That's going to be a 12 square root of u from 0 to 4, and here square root of 4 minus square root of 0, that's 12 times 2, which is 24 units.